And welcome back, my party people. Welcome back to part 2 for simple versus compound probability. So if you are here live or watching this as a recording and you haven't had the chance to watch the first probability session yet, I would really recommend it because we really took time to understand the core differences between simple and compound probability, which really sets the tone for today's class. So I want to make sure that if you weren't here in yesterday's class or you haven't watched it yet, I really do recommend going through it. It was a fun class. We did go over some of those nuances, those basic fundamental notes. And in today's class, we're going to continue that same conversation. We're going to go ahead and understand continuously that difference between the use of the word and versus or when it comes to compound probability. And just like yesterday, we are going to get the opportunity to practice with those test level questions to build up that speed and confidence so that way you're nice and good on test day. So with that, we have the same notes but structured in a different way along with a new little twist to the game for today's class. So let's go ahead and get started here with the first set of notes. So even if you weren't here yesterday, this is the main fundamental piece that takes us, from here moving forward. And that's the definition of simple probability. What makes simple probability simple, my party people, is that we're dealing with one event, one outcome. We are looking for one outcome that we're looking for, and we just divide that by the total possible outcomes. So for example, if we're rolling a 6-sided dice, boom, and we're trying to figure out, hey, what's the probability of landing on a 3? Well, if we're trying to land on a 3, we desire one outcome, the number 3. And since there are 6 total numbers that we could roll, we would divide that by 6. So it would be 1 over 6. And don't worry, we'll get plenty of chances for more examples in today's class. But this is, again, the definition of simple probability. The probability of event A, we'll just say A, B, C, D, yada, yada, yada. But the probability of event A happening is just going to be the number of ways that what we want can happen divided by all the possible outcomes that can happen. Before I continue, my party people, give me a ready in the chat box if we are ready to move forward from here. So let's go ahead and push it over here to page number 2. So this is kind of a two-parter. We have the definition of compound probability with the word and then compound probability with the word or. And so we'll talk about both of these here. So number 1, let's go ahead and talk about the word and. So just as a reminder from yesterday's class, everybody, when we're talking about compound probability, compound means what is the probability of 2 or more events happening at once. So in this case, using the word and, we could use the example, hey, what's the probability of rolling a 2 on a dice and flipping a coin and landing on heads? If we're trying to find 2 things happening at the same time, what we do is we multiply the probabilities. And so one important highlight that I'll make to make your life easier is going to be the word and. When it comes to probability, we are associating that with multiplication. Again, the word and, we associate it with multiplication. So if we say, hey, what's the probability of this and that happening? Again, we are multiplying their probabilities. So with that said, I'll give you a moment to write this down if you haven't had the chance to do so already. And then we'll move over to the next page where we talk about compound probability with the word or. All right, my party people. So from here, let's go ahead and move it on forward. Here is page 3. Let's take a little look here at compound probability with the word or. So where we're basically saying, hey, if we roll a dice, what's the probability of rolling a 3 or rolling a 5? Again, you're basically talking about the same event, but you're talking about more than one outcome that you're okay with. Because everybody, if I say, just like I did yesterday, just like I did in that previous lesson, if I say, man, I could really go for some pizza or I could really go for some chicken Alfredo. Well, the fact of the matter is, what I'm saying is I would be absolutely okay if I had pizza or if I had chicken Alfredo. I don't need both of them. The word or means one or the other. They're both fine. My party people, does that make sense before I continue on to talking about overlaps? Yeah, that's right. Either one is okay. And so we count both of them. So let's move it forward here. Let me highlight the word or, because when we talk about the word or, we are adding their probabilities. Again, if we have these two things that we want to find and we use the word or for either one, we will add their probabilities together. So for example, right here, if we're saying, hey, what's the probability of event A or event B? Again, this could be rolling a 3, and this could be, picking a taco. It really doesn't matter. But if you say event A or B, the way that you calculate that is just find their individual probabilities and then just add them together. That's it. However, everybody, there are going to be situations, and I know some of us are going to have that headache reappear from yesterday, I know, but there are going to be situations where there is overlap. And I'm going to give you a really good example in terms of what that means. So if there's overlap, everybody, in terms of, when we're saying A or B, but some of the events in B could count as A, or some of the things in A could count in B, what you do is you're still going to start the same way right over here. You're still going to add their individual probabilities together. But if there is overlap, you subtract the probability of both of them happening together. Again, you subtract the probability of both events being true because you're taking away that extra overlap. Now, there's no better example than the one right below here. Here's an example. The example says, hey, what's the probability, if we're rolling a 6-sided dice? Let's go ahead and say we have this dice right over here, and we're trying to go ahead just like that. Let's say I'm a really good drawer today, which I don't really think I am, but let's say we're rolling this dice, and we are trying to find the probability of rolling a 3 or rolling an odd number. Everybody, if we're thinking about the possibilities here as 1, 2, 3, 4, 5, and 6, again, down here at the bottom left, if we're considering this, well, everybody, what are the chances of rolling a 3? Well, that's just going to be 1 out of the 6 numbers. And that's where the 1 out of 6 comes from. Now, everybody, let's talk about those odd numbers. How many of these numbers are odd, or which of these numbers are odd? From 1, 2, 3, 4, 5, and 6? Correct. 3 of them. 1, 3, and 5. Those are all odd. Now let me highlight those with a different color. Let's go ahead and use green here. Or not green, excuse me. Let's use blue. Okay, so I'm gonna highlight the 1, I'll highlight the 3, and I'll highlight the 5. Everybody, what do we notice? We just noticed right here that we highlighted the 3 twice. Once for the 1/6, and then again when we counted those odd numbers right here. So that's a little bit of a problem, everybody. That's a bit of a problem because if you count the same thing twice, you're not really calculating a proper probability. You're not. And so we have to take that into account, and we have to fix that. We have to correct that. And that's where this right over here comes in. We'll subtract the probability of both of them being true. Meaning, what's the probability of getting an odd number 3? Well, 3 is odd. So that's just one of the 6 numbers right there. They are both true on one of the 6 outcomes. And that's why right over here, we subtract 1/6. That's where that comes in. So when we do the math here, we have the 1/6 plus the 3/6 for the odd numbers, but we'll take away 1/6 right over here. We'll take that away because this is the overlap. That's what we must get rid of. We subtract overlaps when it comes to the word or. And again, that's only if an overlap exists. And you really have to pay attention to each situation to understand that. But before I continue, everybody, here's the gist of it. Here's the premise. The premise is when you're using the word or for compound probability, when you're using the word or, You're just going to add those probabilities together. And if there's overlap, you simply take that into account by subtracting where both of those events are true. So with that, once we do all the work here, 1 plus 3 minus 1, that brings us back down to 3 over 6, which will turn into 1/2. And that's correct, Ruben. Yes, the word or is affiliated with addition, and then the word and is affiliated with multiplication. Exactly. And so one more question here. When we're trying to understand, how do we know if they overlap? That's where it really boils down to your ability to pay attention to the context. So in this case, I think we can all look at this and say, hey, if we're trying to roll a 3 or an odd number, well, 3 is an odd number. So that's overlap for sure. And now we have to take into account those other situations, whether it's a deck of cards, whether it's a spinner, whether it's drawing sticks or different colored balls from a bag. We have to take into account all of those different situations on a case-by-case basis. And I know that sounds a little muddy, for sure, but this is where we grow by giving our best foot forward every time. All right, so with that said, my party people, we are going to continue forward here, and we have one more page of notes, but we are actually not going to go through this last page of notes, not until it actually becomes relevant. And that's going to be regarding the situations where we have replacement versus non-replacement. So let's have a nice little warm up here, so that way we can just get that understanding nice and fresh right over here. So I got you, my party people. Let's go ahead and give it a shot here, nice and slow. Any word problem, no matter what, we're going to start by reading the question first. So let's read that question here. It says, if one flower is picked at random, what is the probability that it is a daisy? Everybody, can we confirm real quick? We are looking for the probability in this specific problem. We want to know the probability of picking a daisy. Do we understand that so far? Is that clear? Even if we are confused on the overall subject today, does that make sense? We're asking for the probability of randomly picking a daisy. Sweet. And what we'll do is we'll go ahead and write down that we are looking for the probability of picking a daisy. And so, remember, this is a simple probability problem. This is going to be our warm-up here. And remember that to calculate probability, we are going to find all the ways that we can get what we want, and we'll divide that by all possible outcomes. So let's go ahead and get this done here. Everybody, what do we want? Well, we want to pick a daisy. When we read the actual context, it says, in a garden, there are 10 tulips and 5 daisies. So my party people, how many daisies are there to pick from? Correct, right here. We see clearly that we have 5 daisies that we can choose from and satisfy what we're looking for. So let's go ahead. Let me draw another bar here so we have a fraction, and I'll write the number 5. Because again, there are 5 daisies. And then from there, we are going to divide this by all the possible outcomes. My party people, how many total ways or total possibilities are there to choose from? How many flowers can we pick from? Yes, correct. If we're saying 15, that is absolutely correct. And that's because to get all outcomes, you add all the possibilities that you see in front of you. So we have 10 tulips and 5 daisies, and that makes a total of 15 flowers. So that'll be, again, right over here, we have 10 tulips plus 5 daisies, and that's going to give us, again, 15 total flowers. And so from there, that's where we have the 15 right there in the denominator. Now, we can't end the problem here because when it comes to the multiple choice options, we're going to be looking forward to, selecting an answer choice that is in simplest form. Remember, you can have a million different fractions that are the same thing. So when it comes to standardized tests, we need to place or write everything in simplest form because that's how, it's a standardized test, and that's how they have to write those final answers that are fractions. So with that, everybody, what number can go into both 5 and 15? What can we divide out of both of them? Correct, we can divide 5. So let's move forward here, divide the 5 by 5. And let's divide the 15 by 5. Once we do it with both, 5 divided by 5 is going to give us 1. 15 divided by 5 gives us 3. And there we are. That is our final answer, 1 out of 3. And so, in terms of the question here, the probability that we select a daisy when choosing at random is a 1 in 3 chance. So every 3 times you pick, it is guesstimated or generally true that you'll get 1 daisy for every 3 flowers that you pick. So with that, everybody, this question again, this one was a very straightforward one. This was not compound probability because notice we're not asking for the probability of selecting a tulip and a daisy or a tulip or a daisy. This is just a straight up simple probability where it's just one outcome that we want. So let me know if that makes sense, my party people. And the last question here, yep. Again, just as a reminder, when it comes to probability, yes, we are dividing what we want divided by all the possible outcomes. Absolutely. All right, my party people. So with that said, let's go ahead and try this next one together. We're going to kick it up a notch because, again, we have done all of the pleasantries in that previous class. And so let's go ahead and try this next one where it's compound, but I'm not going to tell you which way. We're going to work on that together. So here's the first thing I want y'all to do. What I want you to do when I show you this question is let me know what key word you're going to hone in on to guide your thinking. Here's the question. What key word are you going to really hone in on here? Yeah, we are going to hone in on the word or. So let me go through this here. So the question reads, what is the probability that the die shows an even number or the spinner lands on the letter A? So take a look. We are looking for probability. That's clear. That's what this class is about, right? But it says, what is the probability that here's event 1, the die shows an even number, or, again, that's the big word, or the spinner lands on the letter A. So take a look one more time. This is how we know that we're dealing with a compound probability problem, specifically with the word or, because we ask for 2 probabilities. We ask for this probability, the dice landing on an even number, or the spinner landing on the letter A. So that's how we know the word probability with the word or separating those events. So with that, let's write this down. As a reminder, everybody, when we want to find the probability of event A or event B happening, so event being even number or landing on the letter A, what we're going to do is we're going to find the probability of rolling an even number, and then we are going to add that with the probability of landing on the letter A. And then we have to take into account, just in case, we have to take into account if there is an overlap or not. And here's how we're going to understand whether there's an overlap. Everybody, when we take a look at, rolling the die or spinning the spinner, is it possible to get an even number and A on just this one or just this one? Correct. No overlap at all. No overlap possible here. So in this case, what we are going to do is we are going to simply add those probabilities together and we are good. Or so you might think, because there actually is overlap in the sense of, hey, yes, there is a possibility where, yeah, you'll land on an even number and you'll get A as well. And we have to actually take that into account. So I wanted to lead off by just playing towards that naiveness where we don't think that there's overlap here, but yes, there actually is. And I'm going to be explaining that as gracefully as I can. So let's go ahead and get into it, everybody. Let's first start off with the dice, and I'm going to show you where that overlap comes into play. So everybody, let's go ahead and say that we are rolling the dice and we're trying to get that even number. We have 6 options. 1, 2, 3, 4, 5, and 6. My party people, how many of these numbers are even? Yeah, 3 of these numbers are even. we see that we have 2, 4, and 6. These are all even numbers. And so with that, we have 3 even numbers out of 6 total numbers. That is the probability of rolling an even number. Next up, we are going to add that with the probability of looking at this spinner here, where this spinner is divided into 4 equal sections labeled A, B, C, and D. Okay, sounds good. So let's go ahead here and draw a little spinner right there, nice and easy. Let's break that down into 4 spots, A, B, C, and D. Everybody, how many ways can we land on A? How many ways can we land on A? Yeah, just once. Just one way. You look at the 4 options, A, B, C, and D, but we're only looking for A. That's just one out of the 4 total possibilities. So when we add this up, we're going to have 1 over 4. So before I continue, my friends, do the individual probabilities make sense for rolling an even number? That's 3 out of the 6 possible numbers. And then with the spinner, that's just one A. Again, A is one of the 4 letters that we can choose from. Awesome. Yeah, I want to make sure that this beginning part makes a lot of sense before I introduce the overlap that we want to take away. So here's where that overlap comes in. And I want to make sure I'm very clear about this. So individually, everybody, when we roll the dice, sure, 3 out of 6 options. When it comes to the spinner, individually, again, if we're only focusing on the spinner, yeah, for sure, that's 1 out of 4. But there is that chance, there is that situation or the event where we roll an even number and we spin an A. Because remember, everybody, what did we say about the word or? Doesn't the word or mean that this or that would be fine? Is that not true? Is that not what we said? Yeah, that's what we've been saying. The word or means that we're okay with this happening or this happening. Like, we can get an even number. So for example, let me make a little more sense for you. So let's say we rolled a 4, but then we spun a C. Do we still succeed, everybody? If we rolled a 4, but land on C, does that still work? Is that still a success? Correct. Yeah, it is. Because again, of the word or. So we can land on a 4 and land on C, and that's still fine. Even though we want A, it's fine because we said either or is okay. Now let me flip it over, everybody. What if we land on a 3, but we land on A? If we land on 3, an odd number, but land on A, is that acceptable? Is that acceptable? So I see a lot of us saying no so far, and that's where I'm so glad I'm doing this early. So the answer is going to be yes, because remember, the word or means that if we get an even number, then the whole thing is good already automatically. If we get an odd number, that's not an even number. But if we land on A, it's still all good. Remember, it's this being true or this being true. That's okay. Either one can be true. But there are events where if they're both true, that's actually going to cause an overlap. And so with that, everybody, we have to take that overlap away. Remember that the overlap is the probability, right over here, the probability of them happening at the same time. Even and A. My party people, when we saw the word and, what operation are we using? When we see the word and, correct, we are using multiplication. So this is where we would do 3 over 6 times 1 over 4, and we'll subtract that at the end. So let's go ahead and handle this together here, everybody. Let's do the math with the fractions, and then I'll go ahead and show you a different example where I hope it'll make so much more sense in terms of why this over here in red is necessary to begin with. Because I know looking at this red overlap part, some of us might be looking at this saying, Coach, what the heck does that mean? I got you. I got you, and I'll make it make more sense very shortly. So here we go, my party people. So let's go ahead and add these fractions over here. 3 over 6 plus 1 over 4. Can someone remind me, how do we add fractions? Thank you, Ruben. Yeah, we're going to find that least common denominator. Absolutely. We're going to find that least common denominator. Everybody, what number can 6 and 4 both go into? What can they both multiply up to? Yeah, they can both multiply up to 12. Remember, we're not dividing here. We're not simplifying. When we are adding fractions, remember that we are trying to get the same denominator. And so we know that 6 and 4 can both go into 12. They can both go into 12. And to get that same denominator, remember that we'll be multiplying the numerator and denominator by the same number. So let's go ahead and do that. Let's multiply the 3 and the 6 both by what to get 12? Yeah, that's going to be a 2. We multiply 6 by 2 to get 12, and we'll multiply the same thing up top. So we have 2 times 3, which is going to give us 6, and then 2 times 6 is going to give us 12. So we have 6 over 12. Now over here on the right side, let's say we have 1 over 4. 1 over 4. All right, my party people. So if we have 1 over 4, yeah, we're going to multiply it by 3. Exactly. We're going to multiply by 3. 4 times 3, that's going to give us 12. And then 1 times 3 is going to give us 3. So from here, we'll proceed to add these together. And once we do so, everyone, what do we get? 6 plus 3 is going to give us what? Yeah, that's going to give us 9 over 12. That's going to give us 9 over 12. So that's what we'll have for right now. We'll keep that right there. But remember, we have to subtract the overlap. So remember, this is counting where it's either even or we land on A. And this also includes where we have even and A. So we have to discount where we double up on that. We have to take that into account. That's what that overlap is. So this is where we're going to turn our attention over here. Let's go ahead and take care of this first. We have 3 over 6 multiplied by 1 over 4. We can absolutely simplify by 3 before we get started, for sure. We can simplify by 3 before we get started. Here, when we do this, we can do 3 divided by 6, dividing by 3 on the top and the bottom, if we'd like to first. Or actually, just to keep things simple, we can simplify it later, that's fine. We can multiply straight across, nice and easy. 3 times 1 is going to give us 3. 6 times 4, that's going to give us 24. And we have that there. My party people, this is what we're subtracting. This is what we're going to be subtracting. So let me write this over here, minus 3 over 24. So now that we're here, everybody, if we want to get this refresher going on subtracting fractions, what do we need again? We need the same what? That's right, we need the same denominator. And what can 12 and 24 both go into? What number can 12 and 24 both go into? Correct, they can both go into, 24. They can both go into 24. So with that, let's go ahead and modify that first fraction nice and easy. Let's multiply the denominator and numerator here by 2 so we can get that 24. So when we move things over, 9 times 2, that's going to give us 18. 12 times 2, that's going to give us 24. And then we'll be subtracting the 3 over 24. All right, everybody, what is 18 subtract 3? Yep, that's going to be 15. And so we have 15 over 24. 15 over 24 right there. And remember, at the end of every single one of these probability problems, we have to simplify. What number can go into both 15 and 24? That's right, 3. We can do 3. So let's go ahead here and divide both the 15 and 24 by 3, and that'll finish things up here. So 15 divided by 3, my party people, is going to be 5, and then 24 divided by 3 is going to be 8, and there is our answer. The probability of landing on even or landing on A is going to be 5 over 8. So I'm going to give you a moment here to take these notes down, take a screenshot, and from there we will try a much more less intense problem for sure. I got you. So to go ahead and alleviate some of the headaches with understanding, wait, why do we actually have to subtract an overlap? I got you. Let me go ahead and show you right over here. So everybody, for example, let's go ahead and say we are rolling a dice, okay? Let's say we're rolling a dice, and then let's also say we are gonna flip a coin. All right, my party people? Let's say we have a dice that we're rolling and a coin that we're flipping. Let's say that we're trying to find the probability. Let's say we're trying to find the probability of an even number or flipping and getting a heads. Everybody, before I even start this off, answer me this. Do you think it's going to be closer to 0%, closer to 50%, or do you think it's guaranteed that we can get even or heads? Like, what do y'all think when we do this? Like, if I roll the dice and I flip a coin, the odds of getting heads or even, do you think it's 50, 100? Like, what do we think here? Okay, so just for the recording's purpose, I see that a lot of us are saying closer to 50%, 1/2, which is 1/2 or 50%. And so, yeah, y'all naturally understand that this is not guaranteed, right? Y'all definitely understand that it is not guaranteed to get even or heads when you roll the dice and flip the coin. But watch what's going to happen in this problem. Watch this. Everybody, what did we say we do? Help me out. What did we say we'll do when it comes to the word or? What did we say we'll do? The operation that we work under? Correct. It's addition. So let's go ahead and show this. To get this probability, we'll do the probability of getting an even number, and we'll add that with the probability of getting heads. Watch the funky stuff that's about to happen. Watch this here. Everyone, help me out with the dice. Having the 6 possible numbers, how many of these numbers are even? Virginia, I appreciate you. That'll be 3 out of the 6. Absolutely. So let me go ahead and again, the probability of an even number right over here with the dice, we see that we have 2, 4, and 6. And so that's 3 out of the 6 total options. 3/6. Now, before I continue, are we good with that? Because again, half of the numbers are even. That would be 3/6. All good? Sweet. All good. Now, from here, let's go ahead and take a look at doing the coin flip and getting heads. So we have heads or tails. Everybody, is that the same as saying 1/2? All right, yep, absolutely. So yeah, that's going to be 1/2 right over here. The probability of flipping a coin and getting heads is 1/2. So let's go ahead and go through our nativity here, our naiveness, and let's add this together. We don't have the same denominator, so let's work to get the same denominator. My friends, we can go through 2 options here. We can modify the 1/2 to make it out of 6, or we can simplify the 3/6 to get down to 1/2. Either way is fine, but let me just go ahead and do it over here. Everybody, what do we multiply 2 by to get to 6? Yeah, we multiply by 3. So when I multiply by 3, just to change the denominator, we have 3/6 on the left side, plus over here, this is now also 3/6. Everybody, when we have 3/6 plus 3/6, what is this going to be? Yeah, that's going to be 6 divided by 6, which is the same thing as 1, which means 100% chance. Like, this is guaranteed to happen. But everybody, let me zoom out real quick. Does that make sense? Does 100% chance make sense? Like, if I'm rolling this dice and I'm flipping a coin, does that really honestly make sense that it's a guarantee that no matter how many times you do it, every single time you do this little experiment, you're guaranteed to get heads or even numbers? Right, no, that doesn't make sense. That does not make sense. So that's the problem, everyone. That's the problem. What this takes into account is, hey, this only worries about when we get an even number. This only worries about when we get heads. But there are times where when you roll the dice and get an even number, you also get heads at the same time. Remember, the word or means this happens by itself or this happens by itself, but there are times where they both happen at the same time. And if they both happen at the same time, everybody, what's that O word that we've been using? If both of them happen at the same time, that O word, overlap. Exactly. That is overlap. And so we have to take that into account. We have to understand that if they both happen at the same time, like you can have an even number with heads and you can have heads with an even number. That is overlap. You're counting the same event twice. So that's why overlapping, that's why taking overlapping into account is necessary to get the true probability of an event. All right, everybody? So before I actually do the math here, do we understand why it's necessary to do what we're about to do? Sweet. And again, I do apologize for taking things, rather quickly in the beginning. That's something that I don't typically do, but I was just really excited about today's class. I'll be honest with you. I was really excited. And I had like 25 problems lined up. And I said, yeah, they can handle the or situations. And then, you already saw 20 minutes into class, I'm sitting here like, oops. So my fault, guys. So let me go ahead and finish this up here. And then we'll, again, transition into those replacement problems and the other ones. So here we go. Let's go ahead and take into account the overlap here. So we will subtract overlap. And the overlap is, again, going to be the probability of even and heads. So the probability of even was 3 over 6. The probability of heads was 1/2. And we'll just go ahead and multiply them together. So let's multiply those together. We got the 3 over 6 right over here for even. We got the 1 over 2 right over here for heads. So let's go ahead and do this right here. 3 times 1 is going to be 3. 6 times 2 is going to be 12. So from here, everybody, this is what we're going to subtract. So let's zoom on out ever so slightly. And let's remind ourselves that what we had when we did the even plus heads, that was 6 over 6. So let me just bring this on down here, because we're going to have 6 over 6 minus the overlap, and the overlap was 3 over 12. When we subtract these, this is what's going to get us the true probability, the true final answer. Everyone, help me out. What can I multiply the 6 by? What can I multiply the 6 by to get me a denominator of 12? Yeah, that's going to be 2. So let's go ahead and do that here. We'll multiply the numerator and denominator by 2. And that's going to give us 12 over 12 minus the overlap, which is 3 over 12. So everyone, 12 minus 3 gives us what? Yeah, that's going to be 9. So when we subtract those, we are going to get 9 over 12. And here at the end, we can simplify to get the final answer. Everyone, what are 9 and 12 both divisible by? Yeah, they're both divisible by 3. Absolutely. Great stuff. So let's divide by 3 and then divide by 3 on the denominator. And that's going to give us 9 divided by 3 is 3. And then 12 divided by 3 is 4. And there we go. There is a 75% chance, so 3/4. There is a 3 in 4 chance that if I were to go ahead and roll a dice and flip a coin, that the outcome would either be even or heads. There is a 3 in 4 chance or a 75% chance, which is very realistic versus that 100% that we got earlier if we didn't take the overlap into account. So, my party people, does that make a little more sense than it did before I write down the exact situations that you'll use this in? Sweet. And again, I appreciate your patience on that, and I'm glad we can make a little rebound off of this one. But like I said, we'll take the rest of class here and focus on those other types of problems outside of the or problem. But this is how you'll know that you'll need to use this right over here for the overlap. This is how you'll know. When you have two independent things with the word or. So what I mean by two independent events, what I mean by that is having a dice and then having a coin flip, where you have two events, two things happening with the word or. This is how. This is how. All right. So when or is used with 2 events. So this isn't like your standard one where it's like, oh, hey, if we roll a dice, what are the odds that we get a 2 or a 5? That's very different. That's one event. You're trying to find out 2 possible outcomes from one event. This is 2 events where you roll a dice and you flip a coin. Again, when or is used with 2 events, that's where overlap must be taken into consideration. So we must calculate and subtract overlap. So we must subtract the overlap. And again, the overlap is just going to be both of the events happening at the same time. So just multiply those individual probabilities and then subtract it at the end. My party people, is this something that you would like me to put more practice in inside of your course program? Sweet. Sounds good. Let me take a moment here. Let me write that down. And then we'll move forward to the next subtopic of today. Give me one moment here because we're going to be updating our little, games module with more topics and subjects. So let me make sure that probability is on the top of the list there. I got y'all. Sweet. So let's go ahead and move on from that, honestly, true torture. I didn't mean to torture y'all in that way. Typically, it's all nice and light. But with that, let's go ahead and take it forward here to the situations where we talk about replacement. So let's go ahead and turn our attention over here. Let's first talk about this one here. So everybody, tell me, I'll give you 10 seconds, even 15 seconds. Can you tell me what the goal of this question is? And again, we're starting to teeter onto probability with and without replacement. So can you tell me here in this problem, what is the goal? Calculating the probability of what? Yeah, trying to calculate blue, but is it just one event, everybody? Yeah, it's 2 events, exactly. There are 2 events here. And the probability that we're trying to calculate for both of the events is that both marbles are blue. Let me highlight this. We want the probability that both marbles are blue. This is how we're going to interpret this, everybody. This is how we're going to interpret this. The way that we interpret this is we are calculating the probability that we select a blue marble and then we select a blue marble again. Does that make sense, everybody? Before I begin the actual, setup and calculation and all that good stuff, does it make sense when we say that, hey, if one marble is drawn and then another marble is drawn, that's 2 events. And if we're asking that both marbles are blue, that's not or. We are saying we want blue and we want blue. So this is a compound probability implied with the word and. And if you wouldn't, if you'd be so kind, what operation are we thinking of when we think of the word and? Correct. Multiplication. So the way that we calculate, again, probability with and is multiplication. So we are going to find the probability of selecting blue, and we're going to multiply that by the probability of selecting blue. But I'm going to put a very big asterisk right here. I'm going to put a very big asterisk because this is really going to depend on this phrase right here, being replaced. So let's go ahead and go through this one by one, my friends. First, let's take a look over here. Before we get into all of this, let's take care of this first. Everyone, what colors are the options? What options do we have for colors when we read that first sentence? A bag contains 3 red, 4 blue, and 3 green marbles. Yeah, we have 3 colors, red, blue, and green. So let's talk about those options, everybody. How many of those options are blue? Yeah, 4 of those options are blue. What we want blue, and that's 4 of them. 4 of them are blue, perfect. Now, how many total options do we have? Yeah, we have 10 total options, exactly. We have 10 total options because we have 3 red, 4 blue, 3 green. 3 plus 4, that's 7. 7 plus 3, that is 10. There we are. Sweet. So that'll be 10 right there. That's the easy part. Now, when we try to find that second probability of getting blue again, this is where you really have to pay attention. Right here. It says, if one marble is drawn, then replaced. Everybody, what does replace mean? if I go into the bag and I grab a blue marble and then I replace it, what does that mean? Does that mean I throw the marble as far away as I can? Or do I put the blue marble back in? Yeah, we put the marble back in. Exactly. The replacement, so with replacement, let me write this here with the asterisk. With replacement, what this means is we place the item back. We place the item back in, then go again. That's what that means. So here's how this affects the problem. And this is going to be pretty cool once we get over some of the common mistakes that we're going to make in the next problem. I promise you there's going to be a mistake made, but we're going to handle it with grace. I promise you. So everyone, check this out. When we picked, like let's say we pick a blue marble and then we put it back, how many marbles are in the bag now? If we pick a blue one and then we put it back, how many total marbles are in the bag now? Giovanni, correct. It's the same 10. Because if we have the bag, let's go ahead and just, draw this bag, something like that. And I stick my hand in, grab the blue marble, and then I put it back in, there are still going to be 10 marbles to choose from. Because again, I replaced it. I put it back in before I tried again. So the probability of selecting a blue the second time is the same probability. There are still 4 blue marbles out of 10 marbles in there. My friends, does that make a little more sense there? Why we see 4/10 listed twice? Because again, it's with replacement. We put it back in, so there are still 10 total marbles. 4 of them are still blue. We didn't throw it away. We didn't put a different color back in. We put the same thing back in, so we have the original setup, and that's why it's still out of 10. And since we're still looking for blue, we still have 4 on both. And so once we're here, that's it. We're done. All we got to do is multiply, and we are set. So let's go ahead and wrap things up here. Let me go ahead and move this over to the right, and let's calculate. Everybody, what is 4 times 4? Correct, that's going to be 16. 4 multiplied by 4 is 16. And then 10 multiplied by 10 is going to give us what? Yeah, that's going to be 100. Perfect. That's going to be 16 out of 100. But everybody, are we done? No, we got to simplify. That's correct. We have to simplify. So let's go ahead and zoom on in over here. 16 over 100. Now, my party people, 16 over 100. What goes into both 16 and 100? What's the biggest number that can go into both 16 and 100? Correct. That's going to be 4. So let's do that here. Let's divide 16 by 4 and 100 by 4. And we can absolutely simplify by 4 as well, Ariane. It would have been 2 over 5 times 2 over 5, which would have given us 4 over 25. But with the simplification, again, we'll get the same exact answer. But you would be correct for trying to simplify beforehand. But here we go. 16 divided by 4 is 4. 100 divided by 4 is 25. And there's our final answer right there. So if you were to, again, randomly try to pick a marble, put that marble back, pick again, the odds of you getting blue twice in a row, here are the odds. 4 over 25, or a 16% chance. And there we are. So when it comes to replacing the item back in, do we see how the conditions are the same for the next time around? Sweet. Sounds good. So what I would like to do next is I want to go ahead and give you this example problem here. I want you to try this next one, and I want to see how we handle this. So I'm going to give you time to try this one on your own. I'm going to, close the chat as I usually do. I want you to try this out. And remember, if it feels frustrating, it's because you probably just haven't done it before. But once you learn how to do it, I promise you it's something that'll stick with you for a pretty long time. So let me get the timer up here. I'll pause it so that way we can skip over if you're watching the recording. And let's give this next example a shot. So before I begin, everybody, can we confirm that this problem involves, that replacement, non-replacement type of problem? Okay, cool. Yeah, it sounds good. Making sure that we see that clearly here, that it says that 2 marbles are drawn sequentially without replacement. Again, not with replacement, without. So let's go ahead and start with the question sentence and then continue from there. So it says, what is the probability that the first marble drawn is red and the second marble drawn is blue? Ooh, so a little different than the previous problem, right? Everybody, do we remember in the previous question how it was blue and then blue again? But this one is a little different. This one is red and then blue. So notice it's slightly different, but I'm going to show you how to handle it the same way. So here we are. We want the probability of, again, selecting red and selecting blue. But there is something that I'm going to want to write in an asterisk, and that is going to be right down here. Everybody, are we using replacement or are we not replacing the item that we've drawn the first time? Yeah, we are not replacing, right? We are not replacing. Notice how I'm emphasizing the same thing over and over and over again, and it's because it's super important. So here, we are not replacing. Again, we are not replacing the first item. So here we go. Let me go ahead and first calculate the probability of selecting a red, and then we will multiply that, because again, this is the word and, this is compound probability, selecting red and blue. So first red, and then we'll concern ourselves with the probability of blue. And I'm gonna wrap this like I did before with that asterisk and that, that boxed off, so I can handle that once I get there. So let's take it one step at a time here, everybody. When we're talking about that first random draw, how many total options are there? What are we putting on the bottom? What are all outcomes? Everything all together, how many marbles do we have to choose from? 12, that is correct. The way that we get 12 is by adding these up here. 5 red, 4 blue, 3 yellow marbles. 5 plus 4, that's going to give us 9. 9 plus 3, that's going to give us 12. So that's where the 12 comes into play. We have 12 total marbles, and of those 12, how many are red? Correct. We have 5 red marbles. Booyah. So with that said, everyone, here's what we're going to take into account without replacement. So let me just go ahead and go to the previous question, and let me just copy this little drawing that I made, because honestly, this is the best thing I've drawn all day. So let me go ahead and grab that and place it right back here. And let's say that, again, I chose that red marble, but I don't replace it. I leave it out. I leave it out. I take that red marble and I leave it out. So instead of having 12 marbles to choose from now, everybody, how many marbles do we have to choose from now? Yeah, it goes down from 12 before, because again, before we had 12 total, 5, 4, and 3 together, that makes 12, but we take one of those red ones out. So now we actually have 11 now. There are 11 marbles here. But my friends, how many of the marbles that are remaining? Of those 11 remaining marbles, because again, remember, we took only one red marble out. How many marbles are blue? Correct. There are still 4 blue marbles. There are still 4 blue marbles that I'll write down right there. 4 blue out of 11 marbles left. And so if we're asking the question, why are we discounting, why are we taking out that red marble? It's because the problem says so. It says that 2 marbles are drawn sequentially. Sequentially meaning one after the other. So in sequence. So 2 marbles are drawn in sequence without replacement. So what this means here in this red highlight, it means that, hey, we're going to go on try one. We're going to go in here. We're going to pick a marble at random. And we're looking for the odds of picking a red one first. Okay, cool. Boom. Got the red one. We took it out. So now we go from 12 marbles to 11 marbles when we're talking about the second time that we pick. Does that make sense, everybody, before I continue? The reason why we go from 12 to 11? Because we are not replacing. That's why the next probability is affected by the first probability. Yeah, at first I know it might seem a little confusing, but once you wrap your head around it, oh yeah, for sure. This is definitely a doable topic. So also, because it wasn't a blue marble that we selected, it doesn't affect the number of blue marbles that are in there. it's still 4 blue marbles, just like it was before. If they asked us to find the probability of red for the second try, it would go from 5 down to 4. Because again, we're not replacing that red one that we chose. So enough of the over-explaining here. Are we ready to perform the calculations, my party people? Sweet, sounds good. Let's go ahead and do the calculations, and then we'll go to another example where I'll let you try another one. I got you. So here we go. Let's go ahead and perform our multiplication. And there are, again, 2 ways that we can really do this. We can go ahead and do 5 times 4 to get 20, 12 times 11 to get 132. But then we're in a position where we have 20 over 132. So that's going to be a bit of a mess. So what I'm going to suggest is let's simplify first. And so let me move this over here and let me again simplify first. Everybody, if we check this out, is it true that 4 and 12 share a common factor? Yeah, they absolutely do. What number can divide into both 4 and 12? Correct, that is 4. We can divide 4 into 12 and 4 into 4. Absolutely. And the reason that I'm allowed to do this, just a brief refresher, when we're multiplying fractions, these are both going to be up top. These are both going to be on bottom. And so remember that with fractions, we can simplify the top and the bottom. So that's what I'm saying. The 4 up top and the 12 on the bottom, we can simplify. So with that, let's do that here. Let's divide the 4, divide the 4. And so now we'll have 5 over, everybody, what's 12 divided by 4? Correct, that's going to be 3. That is going to be 3. Let me go ahead and put that in purple. There we go. Multiplied by, everybody, what's 4 divided by 4? Correct, that's going to be 1. And then the 11 that we had before stays right where it was. So notice how this is a much, much easier multiplication. Let's go ahead and finish it up here. Everybody, what's 5 times 1? I know, hardest question of the day. Correct, that's going to be 5. And then 3 times 11, that's going to give us 33. And that, my friends, is our final answer. 5 divided by 33. Booyah. So if you had 5 over 33 as your final answer, congratulations, you are correct. Who here was pretty close? Who here was really close? Maybe they just made one tiny mistake that you now understand. Cool. And I'm not saying close with the final answer, because if you missed, discounting or subtracting from the 12, you would have gotten like 20 over 144. And then when you would have simplified, it would have been something like, let me see with some mental math, it would have been 5 over 36 is what you would have gotten, something like that. So it's still somewhat close, but you're good. Now, let me answer a couple of questions here. Some folks are asking, Coach, why do we have 11 and 4? Like, why is this 11 and not 12? So I want to make myself very clear here. Because the problem says, the only thing I highlighted here, because the problem says without replacement, this means that after the first pick, after we pick the red marble, out of all of these marbles, let me go ahead and actually just show you here. Let me zoom on in. We had 5 red, 4 blue, and 3 yellow. So let's go ahead and just do this. 1, 2, 3, 4, 5 red, 4 blue, 1, 2, 3, 4, and then 3 yellow. I'll go ahead and use yellow. Hopefully we can see this pretty clear. 3 yellow marbles. Everybody, can we see all that together? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can we confirm that? Sweet. So on the first time, let me actually erase this here and erase all that. So the first time that we try to select a marble at random, if we were to succeed and pick a red marble, let me go ahead and take that marble out from right here. Whee! And that's out. That is out. So once we take that red marble out and we've succeeded, everybody, how many marbles do we have left inside of the bag to choose from? Yeah, that's going to be 11. So this second probability here, when we're trying to calculate the probability of selecting blue, after picking a red, we see that we only have 11 marbles to choose from now. We only have 11. And we still have 1, 2, 3, 4 blue. And that's why this is 4 over 11. There we go. I'm glad it makes a little more sense. There we go. When in doubt, draw it out, right? So my party people, let me know if anybody else there, if that makes a little more sense for you too. Right on. And again, yes, just to make sure I tie it all together with a nice bow, yes, it's because the problem said without replacement. So that means that we do not put the red marble back in. We do not put it back in. No, no, no. If it said with replacement, then the conditions are the same for both probabilities. You still have the same total as before. So that's the big difference between replacement and not replacement. All right, so here's our next example problem. Let's give it a shot here. Everybody, no matter how you feel, whether you're confident or confused, remember that the responsibility that you have at the very first turn here is to understand the goal. Or, in other words, read the question. So when we do that, tell me in the chat box, what is the goal of this problem? What is the probability that the first marble drawn is green and the second marble drawn is red? Everybody, what's the goal here? What is the goal? What are we looking for? What do we want? We want what? Yeah, we have two probabilities that we're going to multiply together because of the word and, but in English, before we try to, complicate things with the math, in English, we are basically picking twice. And what do we want first? When we pick the first time randomly, what do we want? The first color we want is green, correct. The first number we want is green. And then the second marble that we want is what? Correct, it's gonna be red. So again, just keep it simple at first. Keep it simple. We want green first. Again, what is the probability that the first marble is green and the second marble drawn is red? So what we want is the probability of green first and then red second and red. And as a nice little reminder to myself, because we all know, not that good at math, when we see the word and when it comes to probability, everybody, the word and tells us what operation? Correct, multiplication. The word and signals multiplication. So if you understand those ideas, that the word and means multiplication, and you read the problem correctly in terms of getting green first, red second, that's a good start. That's a good start. And from here, I can help you take the next steps. Let's go ahead and do that. So when we read the problem here, here's what we need to understand. The first sentence gives it all away. The first sentence says, 2 marbles are drawn consecutively without replacement from a bag containing 5 green and 7 red marbles. Again, the most important part is this. 2 marbles are drawn consecutively without replacement. So back to back is what consecutively means. One right after the other, exactly. So 2 marbles are drawn back to back without replacement. So everybody, let's go ahead and draw that bag again, right there, our magic bag. And I'm gonna make it a little bigger there. And let's go ahead and fill it in here. We have 1, 2, 3, 4, 5 green. And then we are going to have 7 red marbles. So here we're gonna have 1, 2, 3, 4, 5, 6, and 7. Okay, so everybody, we have our bag here with the green and red marbles. We have 5 green, 7 red, as the problem tells us. So we're good. But the problem is that we are not replacing the first marble that we pick. We are not replacing it. We have got to keep that in consideration because the word and is going to tell us to take the probability of green and then multiply it with the probability of getting red. But again, it's without replacement. Let me put an asterisk there. It's going to be without replacement. Without replacement. Just like that. So let's get into it here. Let's begin with the simpler one, the easier one, which is just finding the green. Everybody, help me out. Let me use the probability down here. So how many total marbles are we selecting from? Yeah, right now it's 12. Again, 5 green, 7 red. That's going to be a total of 12 marbles, nice and easy. And how many of them are green? Correct, that's going to be 5. So that's the easier one, right? It's just 5 over 12. Sweet. Now, here's where it gets slightly more complicated, everybody. Here's how we're going to handle this next one. So first, let's understand the context. We are picking 2 marbles back to back. The first marble, after we pick it, we are not replacing it. Does everybody understand that? Yes or no in the chat box. Do we understand that we are not replacing that first marble? Good. So let's go ahead and exemplify that. Let's show that. Let me grab a green marble here, because again, that's what I'm trying to pick at first. I'm going to grab a green marble. Whee! Picked it up. Cool. And I'll put it on the side here. Once I do that, everyone, how many marbles are left in the bag? Yeah, there are now 11 marbles left. So we have 4 and 7. That is 11 left. Can we all confirm that, everybody? 11 marbles left to choose from? Because again, without replacement. Exactly. So cool. We'll go ahead and have 11 that we're choosing from now. Because again, we didn't replace it. But how many of them are red? Yeah, there are 7. There are 7. Because again, let me go ahead and just zoom on in here. This is 11 after a marble is already selected. After a marble is selected, we are not making it available to be chosen again. So that's why we go down from 12 original marbles down to 11 in the second probability, because we're choosing from what's left. We're not resetting everything. We're simply choosing from what is left. And so there are 11 left. There are 7 red in there remaining. Booyah. 7 over 11. Once we're here, we are ready to multiply. And once we multiply, we will have our answer right away. Everyone, 5 times 7 gives us, correct, that'll give us 35. And then 12 times 11, what will that give us? Correct, 132. And there we are. We have 35 over 132, and that is our final answer. It is C. And there we go. So who here was a little nervous that they wouldn't get this one right, but you ended up getting it right. Excellent. Right on. And to answer the question that I saw there, almost slipped by, but Queen, your question was, hey, why do we take out just 1 marble, but the paragraph said 2 marbles? Hey, valid question. Valid question. And that's because we have the second marble being chosen, which is the red one. So we can absolutely go ahead and visualize it by taking a red marble and taking it out. Whee! Right over here, and there we go. But we're not doing any more work after this. So there wasn't really a reason for me to kind of show that. But if we were to make a third pick with the remaining marbles, then yeah, we would have to show that second marble being chosen. But we already chose the first marble, the green one, and the second one chosen was red. So does that make a little more sense, my party people, and to you, Queen, the person who asked the question? Sweet. Sounds good. Let's go ahead and give another problem a shot here, everybody. Let's keep it going. And let's give this next one a shot here. Let's keep giving it our best foot forward. So, everyone, what is it that we want? The probability of what? What is it that we want? Yeah, we want both marbles red. We want red twice. Exactly. We want to randomly select one, pick red, then randomly select another, and then pick red again. However, my party people, what is different about this question versus the previous 2 that we've tried? What's different about this one? Correct. It's being replaced. The marble is being replaced. So I love that we landed on this problem here, because I'll be able to show you what's going to happen here. So let me go ahead and paste my handy dandy bag here right there. Let me go ahead and just obnoxious there on the right side. So let me go ahead and place 6 red marbles. 1, 2, 3, 4, 5, and 6. And then we have, oh Lord, we have 14 blue ones. Okay, bear with me. We're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 blue marbles. So can we all confirm that we have right now 6 plus 14 being 20 total marbles? Can we confirm that for me? All right, perfect. So let me go ahead and use a different color to highlight this. I'm going to highlight that they are replaced. Everybody remember, the word replaced means if I were to choose a red marble, I would put it back before choosing again. That's what replacement is. It's, hey, I'm going to take a marble out for the first try, and I'm going to put it back in and try again. So if I'm trying to get the probability of landing on red and then red again with replacement, let me just write this out again. We are replacing. So replacement is a check. Yes, we are replacing the marble after we select it. So remember that the word and means we will multiply these probabilities together. So we are essentially doing the probability of selecting red times the probability of selecting red after picking the first red. So let's just worry about this first one here. Everybody, if we were to randomly select a red marble, what are those chances? How many red marbles are in versus the total number? Correct, we have 6 red marbles that we can select from out of the total of 20 marbles in the bag. Exactly. Now, let's say we chose that red marble. Sweet, let's put it off to the side. The problem says though, hey, if one marble is drawn at random, okay, cool, and it's red, and we selected it, but it's replaced, we'll put the red marble back in before trying again for round 2. So we have the same conditions as before. Now we're going to select a red out of the same original 20. Everybody, how many reds are in there? Even though we selected red already, we still have 6 in there because we replaced it. So we have 6 in there out of the 20 marbles, and boom, this is where we put in that work and we'll be done. So let's get into it, everybody. We can choose to go ahead and multiply, then simplify, which I really wouldn't recommend. I really would recommend simplifying first to give yourself an easier time, and I'll show you what that looks like. Zooming in here. Everybody, what number can go into both 6 and 20? What can we divide out of both of these values? That's right, we can divide 2 out of both 6 and 20. That's correct. So let me use the color blue here, and let's divide 2 out of both the numerator and denominator. And we can do it here as well. Make things simpler. So we have 6 divided by 2, and that's going to be 3. 20 divided by 2, that's going to be 10. Same thing over here. 6 divided by 2 is 3. 20 divided by 2 is 10. Then from there, everybody, 3 times 3, what's that going to give us? Correct, that's going to be 9. And then 10 times 10 gives us 100. Exactly. And there's our final answer. We're all done. The final answer in terms of the probability of selecting red, replacing it, then selecting red again, your chances are 9 in 100, which is 9%. So if you had this same bag setup, the probability of you selecting red, then red again, is 9%, which isn't a good probability, but still nonetheless, it's accurate. 9 out of 100 is our answer. So with that said, my party people, who here feels like, again, they've made a little bit of a stride here, specifically when it comes to replacement versus non-replacement? Do we feel like we're trending in the right direction at the very least?